My talk is Demystifying Elliptic Curves. I'm Asher. I think a lot of people already kind of know me as from Clubhouse, so you might have heard my voice. But I actually kind of wanted to start building stuff and not talking about building stuff. So the last couple weeks, I started trying to tackle this topic, which is kind of an area of Bitcoin that I've always sort of ignored, I guess. I think the hashing part and the mining part is a little bit more glamorous, I guess. And when it comes to the topic of how signatures work and how you actually move Bitcoin from one person to another, the signatures part of that, it gets a little hairy, and there are some great educational resources. I don't think Jimmy's in the room, so this is not going to be as embarrassing as I feared, but I actually ended up using part of his programming Bitcoin Python code to build this stuff. So yeah, what I wanted to do was sort of provide a way to to teach the topic of elliptic curves and how they're used in Bitcoin, but we're not going to do any coding, and there'll be barely any math in the way that you might have been taught to do math. So you may not know, but in the old days, before, can you not hear me? You good?
Can you make the text bigger?
Oh yeah. Is this a bit bigger?
Good.
Yeah. Okay, so in the old days, before algebra was invented, there was something called geometry, and that's how mathematicians actually did proofs and stuff, and basically they had straight edges, and they had points and compasses, and they had to figure out everything based on that. So that's the kind of approach we're going to use, in a sense, so we don't have to sort of look at the syntax or get confused by the syntax of what's going on so much. I'm using this website called GeoGebra to build this whole lesson. The lesson's going to be split into two halves. First is the continuous curves description of elliptic curves, and then the second half is the kind of the finite discrete form of that, which is what's actually implemented in Bitcoin. Elliptic curves are described by this following expression or equation. This is almost the only algebra you'll see, but basically what this is saying is that for every point along this curve, that point satisfies this expression. So if I click a point here, I can move this point along this curve, so for the x and y coordinates of this point will satisfy y squared equals x cubed plus this parameter a times x plus this parameter b. So a controls the curviness of the curve, let's say, and b controls, let's see, what does b? Oh yeah, so it kind of squeezes everything down. And even if you actually make it small enough, it'll split the curve in twain. So that's it. That's the end of the talk. No, yeah, there's more. Okay, so there's this other point down here called it's called the negative of this point. Even though traditionally, if you just multiplied this point by the negative value, you'd end up over here. But what we're going to call point negation is this idea of reflecting this point around off of this axis. So for every point up here, there's by definition a point down there, and vice versa. So if I grab this and pull it down here, you'll see we'll end up there for that point. Okay, so in Bitcoin, this equation is even simpler. A equals 0 and b equals 7. So when a equals 0, you just get x cubed plus 7 here for b. So it's pretty, that's going to come up a lot. All right, so now I'm going to introduce this idea of a point addition. And remember, this is before algebra. So addition is something that we can just assign a meaning to. So in this case, addition is going to mean if we have 2 points, P and Q, we can draw a straight line through those points. And that straight line is going to intersect that curve again at this third point, which for the moment, I'm going to call that negative r. We can associate with that point its negative, which is this positive r down here. So what we're saying is p plus q is going to equal r. That's just what addition means to us now. A couple of things to note is for any 2 points you choose, there's always going to be only one other point that it touches the curve, at most one other point. So, even when I bring p below q, so what happens if p is directly underneath q? What do you think is going to happen? Does anyone want to blurt it out?
Straight. It'll intersect at infinity?
Yeah.
Just 2 spots.
Yeah, so there's okay, so you could say, there's 2 ways to say this. One, you could say it doesn't intersect the curve at all. And another is to say it intersects the curve at infinity. And that's how mathematicians like to describe it. That yes, there is an intersection and it's somewhere infinitely far away. And then the second thing we want to note is what happens if p is equal to q? So in other words, what's p plus p? So as we bring these 2 closer together, you'll see that this line approaches what's called the tangent to the curve. So for any curve, if you pick a point on that curve, you can define the tangent, or like where the line that just touches that curve. So that's it. That's how we define addition. And so next we're going to talk about multiplication. So just as we said, okay, we can start. Oh yeah. So we can say what is the idea of like, what if we just took this tangent at this point and we found where it connects like that r, and then we did it again. We started at that point r and we found the next tangent and we hopped over to the next point. And we could do this iteratively. We could do this like n times. And I'll show you what the path would look like. So we start at this G0, which let's just call it the generator point. And we could hop over here and then down here. So this would be G times 2, or 2G. And then we could hop over here and down again, and this would be like G times 3. Now, if I didn't show you the path and you just see like G0 and Gn, it would be very difficult to guess like what the n was, like how many times did I hop around before I ended up here. So as I drag this around, you'll see like it's just like not obvious what the connection is between these 2 points. And it's only until when I show you the path that that you can walk the path. There's something very like zen about that. So the fact that like you can't just guess what n is called the elliptic curve discrete log problem. And it's sort of analogous to not being able to guess what 2 prime numbers you have if you multiply 2 big prime numbers together. That's the discrete log problem. This is the elliptic curve discrete log problem. And this is like the fact that it's like virtually impossible to reverse. Like when n is small, like it's just 3 in this case. It's sort of like an easy to guess. It's like we could just brute force this and end up at this point G sub n. But if n is large, it becomes intractable. So what I write here is like the security of elliptic curve cryptography depends on this being an irreversible problem. So like, and you'll see later like the implications of that, but essentially like if you break like SHA-256, you could basically produce blocks willy-nilly, right? But if you broke this, you could just move everyone's funds to whatever account you wanted, like trivially. So so that's why, yeah, I can't stress the importance of the fact that like both is an unsolvable problem to go back, but as far as mathematicians know, but also, yeah, it's important to get the math right here. Okay, so we saw this in the continuous space, and now we're going to start talking about, or introduce the concept of finite elliptic curves in what we call finite fields. So I started building this like talk was trying to do everything in GeoGebra, and I kind of pushed the limits of what you could do in GeoGebra when it comes to like this notion of so basically, I mentioned we want to do this on computers, and in computers we can't just talk about infinite numbers or arbitrarily large numbers. We have to squeeze things into a finite space. So we could say, like, what if we took this curve and just try to squeeze it into this box here, and then we only consider like the integers modulo this point 7. And then if you try to do that with the continuous curve, you kind of break GeoGebra. So I was like, all right, we need a different approach to like teaching this point. So first I say that the great thing about finite fields and elliptic curves is that they have the same geometric properties as in the continuous case, and you can click on this link and that'll give you like a paper, math paper, if you know how to read math. Then it'll explain like why that's true. But for us, we're just going to sort of take it for granted. And so I started trying to implement this, like a finite version of this in on this website, this GitHub link. So I'm going to switch over to that. So it's essentially it's a web app that runs in a Docker container. So it's pretty easy to spin up if you want to do this yourself or if you want to teach it to other people. So feel free to contribute to this. This is like by no means complete. All right, so we have that expression before, as we say again. So where we can choose A and we can choose B. So by default, it chooses it's set to 0 for the Bitcoin parameters. Sorry, I have debug mode on. We can also choose this. The size of the space where we're squeezing these points in. And so what you're looking at is, I should say that all these white points are the locations where the integer values for, like, say this point, 1855, that satisfies this expression modulo the boundaries of this box. So when I say modulo, think like Pac-Man rules. So you know how, like, in Pac-Man you go off the screen, you come back on the other side? It's the same concept, but it makes it much easier to reason about, like, the space of points we're talking about. And then the second thing is, like, this modulo that we're choosing, we happen to be choosing a prime number for the modulus. So I've gone ahead and pre-computed the first 100 primes. Took me all day, but yeah, so like 67 is a prime number, turns out. But we can squeeze this down. I think by default it's 37 is the space. And the number of white points is given here, in this case 39. I need to be looking at my time. So, and then the last thing about just talking about the size of the space is that, how much more time what time is it?
11:48.
Okay. Cool. Yeah, the last thing I'll say is that in Bitcoin, the prime space that they're in is like a ridiculously huge number. So this is like the number of points, I think, in the curve that Bitcoin uses. So it's like on the order of the number of atoms in the universe size. So when I had said initially that, like, we're not going to be doing small n, like, this is like, I was putting it mildly. All right, so just like we had point addition, oh, yeah, I didn't actually show you point addition. So I can take 2 points, and it'll give me a third point. And if I take, so that's this green one down here. And so you could play around with this and see, like, yes, we do indeed get one unique third point. And also, if I take a point and the point below it, I get infinity. So you add these two together, you get infinity. And also, if I take 1 point and the same point twice, you get something like the tangent. So it's hard to describe, like, the tangent in a, like, you don't really see the curvature of this thing at all, but you can represent this algebraically, and basically the moral of the story is, like, you still get a point that represents the addition of a point in itself. And just like with addition, we have multiplication. We still can define that. So if n equals 0, we get a point that's effectively like not on the plane. So it's intersects at infinity. If you choose n equals 1, we get the identity. And we can hop around here. And something to note is that like we can essentially reach all of these points if we start here. But if we, at this point, 925, we'll eventually cycle through all 39 points. But if we started here, say at 1820, you see that we can only actually reach 13 of the 39 points. And in fact, if we show, that's called the subgroup of this generator. And so all these green points represent the subgroup of this field. So yeah, that'll be important later. Okay, so what do we do with all of this information? Well, we can actually start building applications based on just that. So, so this is our proverbial like Alice and Bob story. So Alice notices that like, wait, if this is it, you can't just reverse like guess what n was given some point, right? So what if I just say like, if I start here and I have a private number, which I'll call my private key. So this case, my private key is just the number 5. I can multiply it by this starting point and get this ending point, and I can share this. I can like tell someone else, hey, this is going to represent my public key, and you'll never guess what my private key was if I just tell you this number. And so she's so excited, she like tells her friend Bob. She's like, hey Bob, like, give me your public key. And he's like, all right, I'll follow your same procedure, and so now I have a public key too. And then Alice is like, wait a second. So she does some math that, and then realizes like, wait a second, we could actually start using this for some cool stuff. Like, we could make, like first she notices that if she takes her private key and multiplies it by Bob's public key, that's represented by HB and her private key here, she's going to get the same thing that Bob would get if he took his private key and multiplied it by her public key. Because if you plug in the definition of Bob's or Alice's public key in here, you'll get the same result whether you're looking at it from Bob's perspective or Alice's perspective. So she's like, hey Bob, tell me your public key. And he's like, it's 2420. So she looks up 2420, puts it in here, multiplies it by her private key, which is 5, and out pops the number 61. And she's like, this is awesome, Bob, like you do the same thing. And he's like, okay, what's your public key? 176. So he looks that up. 176 is down here. Yeah. He multiplies it by his private key, and he gets his own answer for this. And she's like, great, so we should have the same shared secret now. So let's do some, we can do some private messaging. So she's gonna write, hi Bob. She's gonna encrypt this, and she can also decrypt it with her same shared secret. She just like go back and forth. So she's gonna encrypt it and she's gonna send this to Bob. And Bob's like, oh, I got mail from Alice, great. She's like, okay, you should be able to decrypt this with our shared secret. And he's like, oh, I can't. There's something, this isn't working. I can't decrypt it with the secret I generated. So can you guess why? Anybody know? Or not guess, but what went wrong here?
They have different shared secrets.
Yeah, but it's supposed to be a shared secret. Like, why could they not compute the same?
They didn't share any information to be a constant.
To be a constant?
A constant between the two.
Yeah.
There's an additional piece of information that you need to share.
Right. So back in the first step, remember when Alice was like, I'm going to make a public key. And she's like, Bob, you make a public key. What did she chose, her generator point, she chose to be 421. His generator point was 1324. So they're using different schemes to represent their so-called public key, private key pair. So she's like, Bob, maybe, okay, instead of 13, whatever you did, use 421 as your generator point. He's like, okay, now we'll have to go back through like the math again. So, what's your public key now? Your new public key? And he's like, it's 3217. So she goes over here, 3217, and he's like, what's your public key? 176, correct? Okay, so now let's try our instant messenger again. So, can you read me? Alright, send, got mail, decrypt. He's like, yes.
Alice is salesy.
Okay, so yeah, so this is to illustrate that with them having only knowledge of their pub keys, they can at least start the process of having a way to encrypt and share their information. This doesn't actually guarantee, though. Doesn't guarantee their identity. So this is what Nadev was saying about signatures. So I started building a whole tab for just the signatures part of this, and I didn't have time to finish it. But that's sort of a teaser for where this project is going. I want to sort of take the different parts of Bitcoin scripting and stick it in here. Oh, and I have a special guest speaker to come in at the last moment. Okay, so this is Silas, the cryptographer. He was really
a cryptographer.
not yet a cryptographer, but he wanted to show you one other application that you can do with this.
Can I remove this?
You can, yeah. This is send a blank message. Oops. There we go.
Okay. Decrypt.
Okay, you can't decrypt nothing, so. Yeah. Alright, what do you want me to type?
You can actually encrypt. You can encrypt a message, and then use that message as it something important, and then encrypt it again. Then there's 2 layers of encryption.
Exactly. So, so you can encrypt it once, and then. Wait, you want to do?
Dad, do you remember the actual thing I did?
No, I don't. You want to just show them multiple layers?
Well, I want to show them the actual application that works for everyone but me.
Oh, no, yeah, that was going to take a while. But basically, what his idea of like you can encrypt and then encrypt again and then again and again. This is something that's utilized in onion routing.
So you can
encrypt one layer to like Bob's public key, and then you can encrypt another layer to
So like what you
John's
can do is you can write down a message like you could write down something like
don't steal
my credit card.
my credit.
You can write that down and then encrypt it, and then you can make that into your credit card number.
Oh, yeah. And that's actually how credit card numbers are shared.
They tell everyone not to steal them.
And yeah. Hopefully they won't steal it. So this is like the end of the talk. Are there any? Anyone wanna?
My credit card number.
Oh yeah. My credit card number is. Do you want to put? Don't put
Credit
it.
card number is.
Words are.
Is your demystifying elliptic curve stuff on GoPro?
Yes. Well, actually, there's a private thing. I'm gonna make it public now. Yeah.
you have the same generator points, can't they brute force each other's keys by just...
If they
That's
check,
the message
like,
right there.
remember I said that
This.
if n is large, it becomes impossible to brute force. So it's sort of like brute forcing SHA-256.
Okay.
It's going to take an enormous amount of energy, like more than power in the universe. Cool.
So
order to tell
then
everyone not to
then you
steal
can
them.
send it, decrypt. He gets the message.
Mm-hmm. Yep. Oh, you put LOL at the end of it?
Yeah. That so you know that it isn't actually her credit card number. Also, I noticed all of these start with D, like lowercase e, and then 5 A's.
Yeah, well, that lowercase g is
And
important.
then what you could do is you could
Yeah, that lowercase g was kind of a big deal.
there
There you go.
lowercase g.
No, decrypt. Yeah. Yeah. Nice.